All right, guys. I hope you've all survived the last 2 weeks and that you've had a lot of fun. Before I get started with the lecture, since this is the last lecture, there's a large number of important people to thank for making this such a wonderful and smoothly running event. And I just want to acknowledge all of them in case some subset of them are here. Whichever subset are here or not, we should clap for all of them. There's Michelle Sage, who's one of the Masters of the Universe in our School of Natural Sciences. You've all interacted a lot with Allison McIntyre, who's been the PIT program assistant, and Mia, the events team, Susan, Abigail, Julianne, Sharon, and Meredith. The AV guys, Sam and Dario, who have, amongst other things, put up with these things going up and down at random intervals. Our staff at the School of Natural Sciences, Lisa, Michelle, Dawn. The dining staff, Chef Michel. How many of you have been served by a French chef for, 10 days of your life? Imagine that's our life here all the time. Pretty good being at the Institute, I have to tell you. Chef Michel, Renee, and the whole staff. The housing and maintenance people that figure out how the hell to house all you guys while you were here, including Sharon Tozigoff. And the Princeton Conference and Events team. They're led by Mariana Boguki. I don't know if I'm pronouncing that last name correctly. Last but most, we should thank Chiara. Where's Chiara? There she is. We should thank Chiara. For giving us these great schools and giving everyone a chance to come enjoy the loveliness of central New Jersey in the middle of the summer, which has a lot of beauties to it despite the 120% humidity that we sometimes have. So anyway, what I want to tell you about in this last lecture, I think there was a relatively broad title of Future Accelerators. That's really a huge topic. So I'm mostly going to talk about a subclass of possibilities revolving around this idea of great big circular colliders, then a sort of next generation of circular machines after the LHC. Liantou talked a little bit about what we can do with Higgs factories, and he said a little about what we can do with the ILC. And I'll have a small amount to say about that too, but I just want to talk about this subset of ideas. In a sense, it's the newer kid on the block in particle physics over the last 3-4 years. People are talking about it and starting to plan for it more and more seriously. Of course, we have to plan for these things 30 years in advance if anything is going to happen. And so this is a good time to be thinking about them. But roughly speaking, we're imagining a machine around 100 kilometers around. And if you take this machine, you could first run it in an E plus E minus mode. It's a lot like LEP in the LHC. So you could first run it in an E plus E minus mode at a center of mass energy around 250 GeV. As Liantou explains, that's where you get a peak of for the Z Higgs production cross-section. And so we can run it as a Higgs factory here, produce millions of Higgs particles, and study their properties in tremendous detail. That's something I'll try to motivate a little bit more, as Liantou did. And then you could also, in a later stage, run exactly the same machine in a proton-proton mode and potentially get up to 100 TeV. And just so you have an idea of what's needed there, let's say you want it tomorrow. Someone gives you a 100-kilometer tunnel tomorrow. They build it tomorrow. Could you tomorrow go and have a 100 TeV collider in there? And the answer is no, because what we need to get to 100 TeV collisions in a 100-kilometer tunnel is magnets are about twice as powerful as the magnets, the magnets that we now have at the LHC. The LHC has 8 Tesla magnets, and the high-field magnet people believe that on the 15-year timescale, they should, with sort of reasonable extrapolation of progress, be able to get to 15 Tesla. Okay? So 15 Tesla magnets in a 100-kilometer tunnel gets you a 100 TeV collider. Okay? So even if you wanted it tomorrow, you're not going to have the magnets for 15 years anyway. And there's not much point putting in 8 Tesla magnets in a 100-kilometer tunnel. It's a big fraction of the cost of the machine. You want to wait till you have the best magnets you have and put them in. So, this, even if we had the tunnel, this is not something that you want to do immediately anyway. And that's why the idea of actually running it in the mode of a Higgs factory first, doing very important great physics while you wait for the magnets to come online, put them in, and then go to proton-proton collisions is a good idea. So what I want to do, since some of this talk, I'm using the computer, even though I hate using the computer because there's a lot of plots in this talk. But I will switch back to the blackboard every now and then to explain a few nice physics points. It's a little strange to try to motivate this, okay? So I don't like talking in terms of physics cases and things like that. It's kind of silly. Why do we do this? Why are all of us in this room? You know, we could be doing many other things with our very mortal, finite life. And we do this thing because that's what attracts us to this subject. Big machines, big physics, big ideas, going to the absolute extremes of what humanity can do to learn something that might be eternally true about the way the world works. If we're interested in smaller potato things, then there's many other things we could do with our lives. But I think this is one of the things that really attracts people to this kind of fundamental pursuit. So that's the most obvious reason. It's the frontier. It continues to be the frontier. We've been doing this kind of experiment for 100 years or 50 years, depending on whether you start with the Rutherford or with the cyclotrons. But in any case, there's no reason to stop doing it now. It's not like they all of a sudden became a factor of 100 more expensive. It's not that the world is ravaged with war and famine and all sorts of other things that is any worse now than it was before. Absolutely no reason for this to be the moment in history where we stop continuing to go to the frontier. And so that's the most fundamental reason for doing it. But in the rest of this part of the talk, I'll give you the more professional reasons for wanting to do this. And it's just a reminder of theoretically what some really big overarching questions are in the 21st century. In the 20th century, we got these two huge pillars of the picture of space-time and quantum mechanics, and we have many reasons to suspect that space-time is an approximate concept, somehow has to be replaced by something else. That's a big zeroth order huge thing, so that's an obvious theoretical challenge. This is a challenge the resolution to it may well involve physics at energy scales that we can't probe with any experiments we can imagine, although maybe as we learn better and better what the nature of the answer to the question is, we might be awakened to the possibility of different kinds of experiments that might probe them. So, but certainly naively, this is associated with physics at the Planck scale. It's very far removed from experiment. Another question that is not obviously disconnected from the first one is how we can get a large macroscopic universe despite the fact that there are violent quantum mechanical fluctuations that would seem to destroy the possibility of sort of coherence on very large scales. And that's yet another way of talking about the fine-tuning problems. At least in the context of the cosmological constant problem, it may well be connected to the question of how space-time emerges, because if you don't have a mechanism that makes the cosmological constant small, well, everything wants to be curled up on the Planck scale anyway. If it's curled up on the Planck scale, it's at a scale where the notion of space-time is breaking down anyway. So somehow, the emergence of something like space-time and a large space-time are not disconnected questions. So they might be connected to each other. It's less obvious how it's connected with the Higgs. But in any case, this is a very basic zeroth order question that we don't have an understanding to. But this one, at least in its avatar involving the Higgs stars on that one. And that's something that we can hope to get some experimental information about. By the way, our friends in astronomy are very excited about, in cosmology, are very excited, as they should be, for taking the big surprise that they discovered back in 1998 that the universe is accelerating, and measuring it to death and really convincing themselves that it looks something like a cosmological constant, okay? And you could say, well, it's just one number, W is just going to be minus 0.97, minus 0.98. No, who cares? If you're an experimentalist, you want to go measure it. You certainly don't want to take assurances from theorists very seriously, because they're the people who are telling you you weren't going to see it to begin with, right? So it's, you've discovered something surprising, and if you're an experimentalist, you pursue it, and you try to characterize it more precisely. The analog of that in particle physics is the discovery of the Higgs, and so far, nothing beyond the Higgs. That's the extra surprise. And so you want to put the Higgs under a powerful microscope and look at it. That's the most obvious motivation. The LHC was powerful enough to make many Higgses, and in a messy environment to discover it in, but it is not powerful enough to really characterize it with with the sort of precision we need to figure out what it's really trying to tell us about this physics. Now, there's a bit of linguistics here. Often when people talk about whether we should build another accelerator or not, they say the obviously correct thing, that unlike the case with the physics of electroweak symmetry breaking and the weak scale, we have no guarantee that new particles need to show up. Okay? Before we discovered the Higgs, something had to unitarize WW scattering, and so we knew something had to happen beneath the scale of 1.5 TeV or something like that, and that is just not true. Now we've seen the Higgs. The theory is in principle theoretically complete up to exponentially higher energy scales than we have access to. And so we don't know where the threshold is for the next particles. And very often people say, therefore, we don't know where new physics is. And so if we can't guarantee that, how do we know we're supposed to build this machine, not another machine? We'll come to that question in a moment. But the sort of underlying thing is, well, is there any point if we don't know what's coming next or where to find it? How can we motivate continuing? And the answer to that is first, the very first slide, because you just go and look to see what's there. That's the nature of this business. But also that in a quite profound sense, the Higgs itself is new physics, all by itself. We've never seen anything like it before. We've never seen, in particle physics, we've never seen a light, elementary seeming spin zero particle. And we've talked ad nauseum for what's strange about having light elementary spin zero particles. There's no discontinuous difference in the number of degrees of freedom between a massless and a massive spin zero particle. Unlike for all particles of higher spin where there is a discontinuous difference, we don't have an understanding for why this can be light compared to heavy high energy scales on the problem. We've seen particles like chiral fermions and gauge fields in condensed matter systems. We've never seen, without a lot of explicit fine-tuning in the system, we've never seen something like an elementary scalar. So this is something new. We haven't seen it before. And we're confused about it, as last week and this week in many lectures made very, very clear. Theoretically, we're confused about it, but experimentally, it's completely obvious what to do when you've discovered something new, you've never seen anything like it before, and your theorist friends are confused about it. You study it. Okay? You have to study it and look at it closely. And more specifically, the issue is just what we alluded to. We've never seen a point-like scalar, fundamental elementary point-like scalar. Now, what does the word elementary or fundamental mean? As you all know, there is no really invariant notion of elementarity. When we say something is elementary, we just mean that on the scale of its Compton wavelength, it looks like its interactions are point-like. Okay? You don't see form factors. It looks like its interactions are point-like. And so when we say that the Higgs is looking elementary, we mean on scales small compared to its Compton wavelength, it has some effective size that we've looked, some resolution that we've seen experimentally. So what would we literally mean by seeing something? Literally seeing something is bouncing a photon off of it, right? That's literally seeing it. And of course, with the Higgs, we can see it in other ways too. We can see how it interacts with Z's, with other particles, and so on. And the picture I've drawn is really roughly on scale the picture of what it looks like now from the LHC. In other words, it's looking somewhat point-like, but not dramatically so. Okay? And in fact, what we'll ever learn from the LHC, after we're completely done learning everything about the Higgs, would give us with that resolution, the size of the Higgs that we'd infer is perfectly compatible with it being about as elementary as a pion was. Okay, so a pion, we say, is a composite. It's made out of up quarks and down quarks. But in fact, the sort of Compton wavelength of the pion is 1 over 130 MeV, and its size, where we really see that it's not elementary and we see the form factors associated with it, is around set by the rho meson mass. Okay, so we have some ratio here, maybe about a factor of 5. And that's more or less the picture we're going to get for the elementarity of the Higgs after we get to the precisions that we think we'll get from the LHC, let's say 10%-ish precisions on the coupling of the Higgs to the Z, it'll be compatible with roughly the same kind of ratio. In fact, we just take the ratio of these scales squared is a good measure for the kind of deviation that we could look for. So we say that theoretically we're very confused if we see an elementary spin-zero particle and nothing else, but we can ask, do we know experimentally that it's so elementary? And the answer is we don't even know that it's more elementary than a pion. Okay, and a pion was not associated with all of physics going haywire, and maybe there's entirely different things explaining fine-tuning problems, all this theoretical drama. Just ended up being composite, and we will not be able to decide just about that super basic question from the LHC. So that's motivation number one. We would like to know if it's more point-like than a pion. And, by a factor of 10. That's the usual figure of merit when you're making progress in an experiment. You want to see if you can just go a factor of 10 better to really know. And this really is the picture that we'll get from a Higgs factory that makes millions of Higgses and will improve. In fact, this most critical coupling will improve by something like 10% from the LHC down to fractions of down to a few tenths of a percent from a Higgs factory. So we'll really go from this kind of fuzzy picture of the Higgs to a picture that the Higgs will look quite point-like. So either that's what we'll learn, in which case the experimentalists can confirm, yes, the Higgs looks point-like, 10 times more point-like than any scalar we've seen before. Okay, and that's a solid fact about the world, an important fact about the world. Or we see there is some evidence for compositeness, in which case, great, that tells us something else. But either way, we're learning something fundamental that will guide our thinking about what it means theoretically. There is the final thing, which is extremely important. Not only do you want to see whether the Higgs looks point-like to other external probes, but the final test of how point-like the Higgs is, the most incisive test of how point-like the Higgs is if it looks point-like to itself. Okay? If it looks point-like to itself means that there needs to be an interaction between three Higgs particles that, the three Higgses meet at a point in space-time, right? Now, that self-interaction, see, the Higgs is in many ways the simplest possible elementary particle. It has no charge, it has no spin, it only has mass, right? And the simplest possible interaction you could imagine is having three identical elementary particles meeting. But it's amusing that we've actually never seen that interaction in nature before, ever. Nothing we know self-interacts. No elementary particle self-interacts. You can say, well, what about gluons? They change color. What about W's and Z's? They change the SU2 flavor. What about gravitons? What about gravitons? Well, the self-interaction of what about photons? You can check by both symmetry. They cannot possibly have three identical helicity photons self-interact. What about gravitons? Well, the self-interaction we get in GR is 2 positive helicity and 1 negative helicity graviton. So still, there's always a quantum number that changes. Okay? The only particle that can enjoy a self-interaction is the Higgs. Okay? And so on the one hand, looking for this interaction and seeing it would confirm in the most direct sense the point-like nature of the Higgs, and on the other hand, it would allow us to see the simplest possible interaction that's allowed in nature that we've actually never seen before, because this is the only particle that can enjoy it. Now, the LHC will barely be able to tell us that this thing is there. Okay? Depending on how you talk to people, talk about a 40% level measurement, 50% level, 30% level. I think as it starts happening, we'll have a better idea of what it'll really be like, but it's not really incisively going to tell us whether it's there or not. And to do this, you need a 100 TeV collider. Okay? So a 100 TeV collider will make roughly 10 to the 9 Higgses. Okay? So 1 billion Higgses, that's so many Higgses that you will be able to determine that coupling constant to about 5% accuracy. And people talk about whether it's 3%, 7%, but it's about, let's call it about the 5% level accuracy. So we'll be able to see that it's there, and we'll be able to measure it with some accuracy. Okay, so that's it. So we should just go to the frontiers. There's the 0th order motivation, and then the absolutely direct things we're guaranteed to learn are about the Higgs. And these important facts about the Higgs, that a Higgs factory and a 100 TeV collider will help us establish whether indeed the Higgs is as surprising as it would be in the standard model with no other particles around, if it really looks elementary, or if there is some kind of substructure associated with it. And those are just things that we'll, for a fact, learn. Okay? Now, of course, the 100 TeV collider does blast further into the high-energy frontier. And here I just wanted to make the small point, is that since the energy is a factor of 7 higher, let's call it 10, the scale at which you make new particles, the reach is also around 10 times higher. Well, it's actually more like a factor of 5 for some processes, and for other processes it can be dramatically more. It can be a factor of 20, okay? And I'll give you examples of it. And furthermore, because the sensitivity to heavy scales that we worry about associated with the Higgs scales quadratically with the cutoff of the theory, a factor of 10 in energy is really giving us a factor of 100 extra probe into these violent vacuum quantum fluctuations that we're so confused about theoretically. All right, so for the next few minutes, I want to just go over, well, I want to talk about the two obvious questions that you have to address if you're really going into the unknown, where we don't know where the threshold of new particles are. And so there are two questions that you want to ask. First, you want to know about just the raw capability of these machines. What can they do? Okay, so with the kind of technologies that we can imagine happening, what's their actual capabilities? And once you know what the capabilities are, then the question is, are any of these deep questions that we're worried about, can we think of any of them that will really be robustly probed with this level of precision and energy? So that's kind of a crucial question, right? Again, how do I know that I don't need a precision of a factor 10,000 better than I had before in order to settle some question? Or how do I know that I don't need to go to energies 100 times bigger than where we are? Why this factor of roughly 10 to 100 on precision? Why the factor of 10 on energy? Are there questions that amount of leap are going to help us settle, okay? Or at least say something robust about? If the answer is no, then apart from just the motivation of going there, you can't make any extra justification. But if the answer is yes, then that's good, and we have more things that we can discuss. All right. So obviously, I wouldn't be giving this lecture if the answer to this question wasn't yes. But let's see. Let's first talk about the projected capabilities. So first, here's just a sense for how much better a Higgs and Z factory can do on precision couplings, on measuring the couplings of the Higgs more precisely. I should say that the circular Higgs factory can also be run back down on the Z pole, in principle, and depending on how aggressive you want to be, you could get between 10 to the 10 and 10 to the 12 Z's, which is a factor of, 10,000 to 1,000,000 more than we got from LEP and SLC. So that's a mind-bogglingly humongous number of Z's. And so one can imagine doing a lot of interesting precision electroweak physics with them. So I'll say a little bit about the Z factory also in a second. But anyway, these are the sort of fractional deviations in the Higgs couplings to different particles. So that's the poster child where you see this very big jump between the LHC, which is the things in gray, and the Higgs factory. Okay? And if you do go back to the Z pole, then these are the projected, and I have to emphasize, this is incredibly conservative, okay? But these are the projected increase in sensitivity on the S&T parameters, okay? So these are the old ovals for S&T, and these are the small ones are what you could get projected going back to the Z pole at a Higgs factory. The reason these are incredibly conservative is, you see, I'm getting you a factor of 10,000 to 100,000 or million more Z's, but my precision on S&T is only improved by a factor of maybe 10. Okay, so why is that? What does that tell you? What does that tell you when things don't scale like the square root? You're dominated by systematics, right? So and so So people are being very, very conservative when making these extrapolations. One of the problems, for example, one of many problems is you need to know like alpha at MZ incredibly well. Okay? Just alpha EM at MZ incredibly well. And if you just do it in the way people typically do, you get errors just at the sort of part in 10,000 level. Okay? And yet people about 18 months ago came up with a clever way of evading that problem, which is to just measure alpha at MZ by doing a scan of the line shape of the Z, instead of doing what you normally do, which is take it from data at low energies and run it up. Okay? So that can get you another factor of 10. So the alpha is no longer the bottleneck, and you have to think about other ones. Okay? But these projections are very conservative, and one should think a lot what one can do with like a factor of 10,000 to 100,000 more Z's. And I should also say, of course, our theoretical understanding of precision electroweak physics has got to improve to the 3-loop level, sometimes to the 4-loop level, to be able to take full advantage of all these Z's. So that's also theoretically interesting. But anyway, big leap in our precision Higgs couplings, as well as factors of 10, 20 on the S&T parameters. I apologize for a somewhat busy plot, but this is just telling you about what standard model cross-sections look like now at 100 TeV collider. And as always, with these things, annoyingly, they're log-log plots. But anyway, all the even very rare standard model processes start happening frequently enough to care about. And as I mentioned, there's around 1 billion Higgses, 10 to the 11 tops that you can make at a 100 TeV collider. If you're a flavor physicist, 10 to the 11 tops is enough tops so that reasonable, rare flavor-changing neutral current decays of the top becomes something that you can imagine looking for. Even at the LHC, in order to be able to see top FCNCs, which are not already in reasonable theories excluded by other things, you have to stand on your head and build complicated models. Here, very reasonable theories of flavor could give you rates of FCNCs that are visible with 10 to the 11 tops. And again, Lian Tao drew these diagrams, but for probing the triple Higgs coupling, we're looking at the interference between this diagram that actually dominates double Higgs production, even though it's a loop, but it's going through top quarks with a big top-Ecala coupling. But you can see this as a kind of a 10% effect underneath that, and with making 1 billion Higgses, it is enough to be able to extract the triple Higgs coupling to the 5% level. All right, now, before going to even new physics capabilities, I want to mention some qualitatively cool things that happen at 100 TeV collider. Really, for the first time at 100 TeV collider, we get to see the standard model start acting like it wants to look in the massless limit. Okay? We don't even see this at the LHC. As you remember from sort of Hadron Collider Physics 101, massive particles are produced at a Hadron Collider more or less on threshold. Even if you have energies that are vastly bigger than the mass of the particle, top quarks at the LHC are produced more or less at rest. Okay? The typical betas of order 1/3, velocities of order 1/3, something like that. And so we don't see, even WZ's tops, we don't see behave effectively as massless particles. When you get to 100 TeV collisions, it starts being high enough energies that some somewhat qualitative things start happening, and you start seeing it behave. More like massless particles. One of these phenomenon is at very high energies, if you could imagine that SU2 cross U1 were just massless particles, you should see the phenomenon of electroweak radiation, just like we see QCD radiation or electromagnetic radiation. Okay? And the figure of merit for radiation is the Sudakov factor. Okay? So if you have a particle and it's radiating something, the probability that it radiates is given by a Casimir alpha times a log squared of the sort of typical PT of the process divided by an infrared cutoff squared. And what gives us the infrared cutoff here is the mass of the particle. Okay? So it'll be over mw squared or z squared. Okay? So that's the Sudakov factor. That's the figure of merit. The Casimir for electroweak is like you get a factor of 4 there. And so it's growing as a log squared. So as you go from the LHC to 100 TeV collider, that thing starts being significant. And you don't need to look at these plots in detail, but this shows you, for example, something like 20% of all dijets that you produce with PTs coming out at 10 TeV or higher at 100 TeV collider, 20% of these dijets come along with W's and Z's just radiated. Okay? So another effect is that there's a significant top quark content of the proton at 100 TeV colliders, just like there's a significant bottom quark content of the proton at Fermilab, okay, at the Tevatron. So again, if you're talking about high enough energy processes, let's say you want to make some heavy Higgs at 10 TeV or something like that, so that you really need the 10 TeV-ish PTs for some TT bar from the proton producing this guy, then you'd make a mistake of order 1 if you just thought of them as, in the usual way, as not in the proton, and the resumming those logs in the PDF really makes a difference. So another phenomenon is that you can start seeing neutrinos. Okay? So neutrinos are normally just missing energy, but, well, why do we see anything? We see anything because they radiate electrons. Okay? And again, in high enough PT events, you can start seeing neutrinos in this way. And this is just to make it very clear, it's an example from new physics. But imagine you had a Z prime up at 5 TeV. That's what it is in this plot. And here, what you just see are the branching ratios for the 3-body decay of Z prime to nu, but where the neutrinos radiate off a Z. Okay, that branching ratio can get as big as, 3% sometimes. Okay, so that's a very significant fraction of the time that when something decays to neutrinos, it actually radiates a Z, and you can see it. Okay, and this is actually something that can be used as a way of, if you see a Z prime like this, as a way of doing much more, learning a lot more about its couplings. If you have any theory, you can start distinguishing left and right-handed components, all sorts of interesting things from the fact that you can start seeing neutrinos. These effects are barely there at the LHC. But the log squared growth is enough that it starts being a phenomenon that you care about more as you go to a 100 TeV collider. Yes? Huh? The running is not that big a deal. Okay? It's really mostly this log squared. Okay. All right. So continuing with the theme of what we can learn. Going back to the Higgs, here in a little bit more detail is the kinds of couplings that we're going to try to probe. So if you imagine writing down all the higher dimension operators, all the leading dimension 6 operators beyond the standard model that involve the Higgs, they come in 3, really 2, but I'm separating one of them off, 2 different kinds. There's one kind which doesn't break any of the symmetries, global symmetries of the standard model, okay? And if you like, take anything in the standard model, the operator H dagger H is neutral under all symmetries. That's related to the hierarchy problem, right? So H dagger H is neutral under all symmetries. So take everything in the standard model and shove an H dagger H in it. Okay, so take H dagger H F mu nu squared, H dagger H in front of Yukawa coupling, a derivative on H dagger H squared. These are totally symmetric operators. If you have any kind of physics at the scale lambda, there's no reason that these things are not generated. And there's also H dagger H cubed. Then there are the operators that break the custodial SU2 symmetry of the standard model. Okay, and they break a symmetry. So this is a famous one for the T parameter. Even the S parameter operator is something that breaks custodial SU2 symmetry. And you can have various couplings. Anything that involves derivatives on the Higgs in this way breaks the custodial SU2 symmetry. Okay? So these couplings are probed in different aspects of this program. Okay? These things, these totally generic things, are probed at the Higgs factory best. The H dagger H cubed affects the triple Higgs self-coupling and is best probed at the 100 TeV collider. And these guys are best probed sitting on the Z-pole. Okay? So, for example, these things on the Z-pole, that literally gives you T and S, so the deviation of MW over MZ cos theta from 1, the Z photon mixing, and these are deviations in the coupling of the Z to various fermions. Okay? So these are the things that are best probed. And the combination of these things allows you in all these cases to probe the cutoff scale to the up to multi-TeVs. Now, just quick questions for you. Who can give me an example of something? What could generate that operator? What kind of high energy physics could generate that operator? Anyone? H dagger H F mu nu squared. Let's say for glue or for a hypercharge. Yeah, you imagine there's some heavy fermion with a Yukawa coupling, heavy, even vector-like fermion with a Yukawa coupling to the Higgs, and if you integrate it out, you can generate operators like that. What can generate this? What could generate h dagger h times the Yukawa coupling? This is something where you imagine that some of the light standard model fermions are mixing with some heavy fermions, okay? Okay, I don't know what happened to my chalk. But if they mix with heavy fermions and the heavy fermions have a Yukawa coupling to the Higgs, then when you integrate out the heavy fermions, you get operators like that. What I want to stress is that when you generate some of the operators, you very often put them in different places, okay? So very typically, integrating out heavy fermions gives you that operator, it gives you this operator, it gives you many operators, okay? Okay, all right. So that's for the basic capabilities, and now I want to transition to the second set of questions, which is, are there important questions about physics that we don't know the answer to now, that this level of leap in energy and precision are the right amount to sort of robustly address? And there are three questions like this that we've those of us thinking about this have thought of. There may be more, but these are three very obvious ones. And they have to do with the nature of the electroweak phase transition, naturalness, and dark matter. And we're not talking about no-lose theorems in this business. You can probably find loopholes and counterexamples to many of the things I'm going to say. And there's really no point in trying to come up with a no-lose theorem, because it's just not the same as it was with the LHC when we knew that there had to be something there because of unitarizing WW scattering. Nonetheless, as I hope you'll see, it's really very robust, the answer we'll get to these questions. And as far as dark matter goes, it's also rather sharp. We'll either see something or really solidly rule out the simplest possibilities, the very simplest possibilities for what WIMP dark matter could be. All right, so let's talk about these things in turn. So first, let's talk about the electroweak transition. Liantel said a little bit about this. What we've seen from the LHC so far, for a long time, we said something like the Higgs breaks electroweak symmetry. Now from the LHC, we have just wiggled in the little quadratic approximation to this potential around its minimum. But we have no idea experimentally what the whole potential looks like, okay? We have no idea if it looks like this, which is what it looks like in the standard model, or if it has some other wiggles in it. Okay, we just don't know. Now, why is this important to settle? Again, I think if you're an experimentalist, it's obvious. You just want to go, you want to know as much as you can about the potential. You just want to try to measure it. But you might say, look, you're a theorist, you say, come on, why would you needlessly complicate things? Obviously, it's going to be the simplest picture where you just have, it's like Landau-Ginzburg theory, you just write down something analytic, you write down everything, it's allowed by symmetries, blah, 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 right? So the simplest possibility is precisely what you should expect, and anything else is needlessly complicating your life. What I want to point out is that the assumption that the potential is given by this Landau-Ginzburg form is precisely associated with believing that there was a hierarchy problem to begin with. Okay? In fact, that's where thinking about the hierarchy problem came from, is from thinking about the analogies with condensed matter systems. In other words, the logic that tells you should write down everything protected by symmetries, just put them all in with dimensional analysis and so on, that's exactly the logic that would tell you that you need a huge amount of fine-tuning or you have to have a lot of particles above your head. That's exactly what we're confused about. So this is not an innocuous assumption. In fact, until we really know experimentally, if you want to know when experimentally should we be absolutely convinced that there's something like this tuning problem to worry about, we won't know that we have to be convinced by it until we experimentally confirm this is what the potential looks like. Okay? And what else could it look like? Well, maybe there's a quartic balancing against a sextic. Okay? Or maybe it's not even analytic. Maybe it looks something like this. This is a form that you might be familiar with from the Coleman-Weinberg paper. All right? Now, how are these things different from each other? So let me just say right now, the LHC will not tell us. We have no idea whether this might have been the potential, this might have been the potential. The LHC will not tell us whether any of these things, will not allow us to distinguish between these things. What changes between these different forms of the potential? The triple Higgs coupling, okay? because what the potential looks like expanding around the minimum changes. For example, in this model, the triple Higgs coupling is 5/3 bigger than in the standard model, okay? Just calculate it's 5/3 bigger. But we won't know from the LHC if it's 5/3 bigger than the standard model or not. Okay, so we want to know the answer to that question. Just because we want to understand better how electroweak symmetry is restored, if you like, as you go to higher energy. Then there's a cosmological question. How is electroweak symmetry restored as we go to higher temperature? Okay? And if you just take the standard model, you imagine the universe is very hot and it cools, there's just a smooth crossover. There's a smooth phase transition as the m squared goes from being positive to being negative gradually. Okay? So in the standard model, and it actually depends on the Higgs being where it is, if it's 70 GeV, we'd even have a first order phase transition, but anyway. In the standard model, as you've all seen, the picture smoothly goes from there to there. But it could be, if we have physics beyond the standard model, that it changes. And we might have had a first order phase transition. Okay, so if you have a first order phase transition, the picture could look that at some temperature, you actually have, at a slightly higher temperature, this minimum was a little bit higher. Then at some temperature, they become equal to each other. Then at lower temperatures, it slides down to look something like that. Well, sorry, with another, I'm drawing it badly, okay? So I'll just leave it like this, okay? So here they become degenerate. As you keep going, this slides down a little bit more. And the way you go from here to there is by bubble nucleation, right? You have to go over the barrier and produce a bubble. Okay, so that's a first order phase transition. And you might want to know, it could have an impact on your picture of the early universe, okay? For example, many of you know about electroweak baryogenesis. The idea of electroweak baryogenesis needs a strongly first order phase transition for electroweak symmetry breaking. Even independent of anything about CP violation, you need a strong first order phase transition. If you have strong first order phase transitions at around the electroweak scale, maybe a little closer to the TeV scale, but in this neighborhood, it could give rise to interesting gravitational wave signals that you can look for with the future space-based experiments like LISA. Okay? It's in that range for both power and frequency that LISA could be sensitive to it. So these things actually have interesting impacts on how we think about cosmology, even experiment. So we'd like to know, was the electroweak transition first order or second order? We'd like to try to address this question experimentally. And this is something that we'll have no idea about from the LHC, absolutely none. Of course, we can't recreate high temperature phenomenon in a collider, but there's the following simple argument, which is that if there is something beyond the Higgs that makes the phase transition first order, this something needs to have two properties. A, the new particles involved cannot be too heavy. They can't be much heavier than the electroweak scale, because otherwise they wouldn't participate in the electroweak transition. And B, they can't be too weakly coupled to the Higgs. Otherwise, again, they wouldn't touch the nature of the phase transition. So that's why it's a perfect target for a Higgs factory in a 100 TeV collider, because these are particles that can't be too much heavier. They can be hundreds of GeV. It can have hundreds of GeV singlets. I'll give you an example in a moment. It can have hundreds of GeV singlets mixing with the Higgs. We have no idea it's there from the LHC. It can't be too weakly coupled to the Higgs. It has to be at hundreds of GeV, maybe a TeV at most, but it must give you deviations in the precision Higgs couplings at the percent level or more, as I'll show you. And it has to be accessible to a 100 TeV collider for just direct production. Okay, so that's why this is an example of the sort of question that these colliders are the answer for. All right, so let me, can we raise the screen? I need to use the board. I don't know if there's anyone over there. No? Okay. Can you guys see this, or was it equally impossible as when I was looking? Is there enough light that you can see this if I move it? No, that doesn't help. Well, maybe if I just right up there, okay? Okay, I'll do that. I'll do that. It's going to be a slight challenge, but I'll do that. All right. So I want to just give you an example to see how this works. And this is the sort of easiest example to talk about, and it's also one where the effects are easiest to think about and are big. I think in many ways it's also the sort of most natural way that something like this could work. Okay, so let's imagine that we have. So first, let me make a little comment that if we had an effective potential for the Higgs that looked like m squared h dagger h plus lambda h dagger h squared, and there's a sextic term as well, h dagger h cubed over cutoff squared, then one way of getting a first-order electroweak transition is actually if this quarter coupling is negative, that's positive, okay? Then it's sort of easy to see that that's what the picture is going to look like, okay? So, and for it to be strongly first order, you want electroweak symmetry breaking to sort of be dominated, or at least comparable from this part as from that part, okay? So that's what we're going to do. We're going to imagine some underlying theory that's going to give us this as an effective theory. And so how are we going to do it? Well, obviously, we're just going to add a singlet that mixes with the Higgs. So now let me write down a theory of the only dimensionless parameters. So I'm going to add a singlet. So I have this. I have some, let me call it lambda tilde h dagger h squared. And then I have a singlet. So I have a singlet. The singlet has a mass. And then I have a couple of couplings. One of them is like a cubic term. I'll take a dimensionless thing out of it. So I'll work in units of the mass of the scalar, singlet h dagger h. And then I'll have some quartic dimensionless coupling kappa s squared h dagger h. Okay? So now, let me just integrate out this singlet at tree level. If I integrate this singlet out at tree level, then what will I get? Well, I have something like this with two Higgses, h dagger h, h dagger h. So I get a correction to the quartic coupling of the Higgs, which goes like a squared, right? It's like ams squared over ms squared. So in fact, this turns out to be negative. So this is something of order a squared h dagger h squared. But then I get subleading pieces. If I just sort of expand that propagator further out, I have something else, which is a squared over ms squared now times the derivative of h dagger h squared. So that's one of those operators that we talked about, okay? Okay, that's one of the dimension 6 operators. And I also get a sextic term, for example, from this diagram. Okay, so I have two A's here, and I have that coupling kappa there. So these are the singlets. Okay, so from here I get plus kappa a squared over ms squared. I'm ignoring factors of 2, h dagger h cubed. Okay? So this thing is negative. It'll be absorbed with lambda tilde to give me what I called my effective lambda before, so I'm not going to write it down again. So I'm getting the thing I told you before, m squared h dagger h. There's some lambda h dagger h squared. And I have these two higher dimension operators. So a squared over ms squared d h dagger h squared plus kappa a squared over ms squared h dagger h cubed. All right. So let's keep that in mind. And now let's ask for this thing to give me a first order phase transition. What I'm trying to do with this, what I'm trying to do here is show you in this example how precisely demanding that this gives you, it's a big perturbation on electroweak symmetry breaking, is going to force the deviations in the couplings of the Higgs to the Z as well as the particle to both be accessible to the Higgs factory in the 100 TeV collider. But just see why this is happening parametrically. So if I just go back to this picture, I want to imagine the electroweak symmetry breaking is actually dominantly driven by these two terms. Okay, so let me just ignore this one. And so imagine the electroweak symmetry breaking is dominated by these two terms. And so you get slightly different formulas for the weak scale, which is now coming from balancing this against that. So the weak scale would be ms squared times the magnitude of lambda. Since lambda is negative, I'm putting the magnitude there over kappa a squared. The mass of the Higgs squared is lambda v squared, as usual. And the mass of the singlet squared is, which is just ms squared, but I'm now translating back in terms of v, is kappa a squared over lambda times v squared. Okay? So, now, from this operator, derivative of h dagger h squared, we get a shift in the coupling of the z to the Higgs. Okay, if you remember, Lian Tao explained how that works. When you put the Higgs to its vev, this changes the wave function normalization for the Higgs. Okay, and when you go to canonical normalization, it shifts the couplings relative to what you expect. So you get a shift in the z-Higgs coupling, which is given by, well, roughly is given by v squared a squared over ms squared. Okay, so that's so a squared v squared over ms squared. And now here's the point, is that now, but I know what v is in terms of everything. And so if I put all of these things in this formula, I get that this is lambda over kappa. Very pretty. Okay, so the shift in the z-Higgs coupling is given by lambda. Now, we can't make lambda too small, right? Lambda's setting the mass of the Higgs, more or less like it did in the standard model. So lambda's like a third or something like that, okay? And of course, this is a smallish quantity already, 15% at the LHC today, 10% of the LHC today, something like that. So kappa's got to be somewhat bigger than lambda. No problem, right? Lambda's already a quite perturbative coupling. Okay, so this just says to the extent that kappa is a little stronger than lambda, we get a small z-Higgs shift. But we cannot make kappa arbitrarily big. Okay? What's the biggest you could possibly imagine making lambda? 4 pi, you would think, right? That's the absolute limit of perturbativity. Actually, if I write it this way, with this definition of kappa, it's more like 16 pi squared. But anyway, however, you can't go that far. You can't go that far because kappa radiatively induces lambda. Okay? Kappa is a quartic coupling, so just that one loop it radiatively induces lambda. So there's actually a limit on how big kappa can be. So we have to have the kappa squared over 16 pi squared is, smaller than lambda. So that is a limit. I can't make kappa too big. And so that tells you that delta z Higgs is just bigger than something. Okay? Delta z Higgs is bigger than roughly the square root of lambda over 4 pi. That's the absolute smallest it could be, and this is around 5%. Okay? If you put numbers in more carefully, it could be closer to 1%. Oh, but that just gives you the idea that this is the case where if this singlet drives dramatic first-order electroweak transition, you must see a big deviation in the z-Higgs coupling. And furthermore, from exactly the same argument, you discover that we can't make ms too heavy, right? Now, this is even more obvious because well, for the reasons we said before, but anyway, ms is bounded by around 4 pi v and has got to be smaller than around 2 TeV. Let's call it. So you have the scalar, can't be heavier than 2 TeV. You have to have a big deviation in the coupling from the z. And now I need the board back down, actually. Sorry. Can we have it back down, please? I'm really making them earn their. Is there anyone up there? Thank you.
So, Nima,
yes.
in this example, so where did you enforce the first order transition?
The place I enforce it is I said the parameters are such that our electroweak symmetry minimum is dominated by the quartic versus the sextic. Okay, yeah.
Like
So that's right, by saying m-squared development. So that's what I'm saying. If you did a more careful analysis, you can slightly suppress this effect. So it can go from 5% to 1%. So I made it as big as it could be, but in the case where it's as big as it could be, it cannot be smaller than 5%, okay? So that's why it's just making it reasonable that the answer is going to come out at the sort of percentage level. And obviously the singlet can't get too much heavier than the weak scale. Both of these things are pretty obvious. I just wanted to show how it works concretely. And now, so this is sort of more generally what I said. I was giving you in this example, but this is the operator that affects the electroweak phase transition. These are the things that we can measure at a Higgs factory, for example. And we can get these either at loop level or at tree level. I was focusing here on the tree level case. But first of all, the 5% deviation in the Z-Higgs coupling is something, even 1% is trivial for a Higgs factory, which is getting down to the 0.2% level for those couplings, so easily accessible. And now this is the reach for a 100 TeV collider for producing a singlet that mixes with the Higgs. Okay? And so here we expect to have a significant mixing with the Higgs, again, obviously, because it's associated with the, for the same reasons that we talked about. This parameter C is a measure of the size of the mixing, roughly is the ratio of the mass of the singlet over the mass of the Higgs over the mass of the singlet. But anyway, if there's even a mixing of order a tenth, this is the kind of reach we have at a 100 TeV collider. I forgot to say, the luminosity at a 100 TeV collider is projected to be around 3,000 inverse femtobarns, okay? So that's not super aggressive, but people will talk about even higher luminosities potentially these days. But with 3,000 inverse femtobarns compared to 300 inverse femtobarns, for example, at the LHC, you can get a reach sort of into the multi-TeV scale, 4.5 TeV for reach for these singlets. So if they're lying around at a TeV or lighter, you will produce them, okay? So in this example, this thing drives the first order phase transition, and it is totally visible at a Higgs factory indirectly, and then the thing that's producing it is completely accessible to the 100 TeV collider. Okay? But again, it could trivially be sitting around here and totally inaccessible to the LHC. All right. So that was, as I said, that's an easy case to talk about for the electroweak phase transition. There are harder cases where it's induced at loop level, and those are actually harder theoretically as well. It's harder to make them affect the phase transition because it's happening radiatively. But even the most difficult cases that people could come up with, there's always, between the shift in the triple Higgs coupling, a shift in Z Higgs, and direct production of the particles, between those three things, all the even most difficult parts of the parameter space and the hardest theories to look for in this way can be covered. All right, so now let me switch to the second topic, which is about naturalness. And here we've talked so much about the naturalness of the school, I have deliberately 0 slides about the philosophy, other than to say that whatever we learn about it, we're learning something. I mean, either the physics, the scale where the Higgs mass becomes calculable and understood is comparable to the weak scale, or it's much higher than the weak scale, or has nothing to do with the weak scale. It doesn't occur anywhere in our universe at all. Okay, and if this happens, we get a complete understanding of electroweak symmetry breaking and even more phenomenon probably, so that would be spectacular. Of course, it's very overdue at the LHC. And okay, here, if it's true, we might get less direct clues from around the scale about what's going on, but it means either some kind of unprecedented correlation between the UV and the IR, or a breakdown of the reductionist paradigm that, as we discussed, the ultimate explanation for the origin of the weak scale might not be found in the microphysics of our universe. So we don't know which way things are going to go, but it's a big deal either way, and we really need to be very sure about whatever conclusions we're drawing about it. Now, the first thing to say is, what if we're just missing Susie? Say, and this is a stand-in for any natural physics, but what if, we say percentage accidents happen, the moon eclipses the sun, blah, blah, blah. Maybe it's not a big deal, these sort of factors of 10, 20, tuning, 100 that we may be forced into the LHC. You really want to make sure that if there's stuff there and it's just around the corner, you miss it, you're really going to see it, right? So what is the reach for a 100 TeV collider? And this is what it is in supersymmetry. And these are the usual kind of plots you see for example, gluino as a function of the mass of the lightest neutralino, so you're always underneath this line because you imagine you make the gluino and it decays to the bottom of the spectrum. And one of the fun things about making these plots is that finally the axes are in units of a TeV, okay? And the reach is, as you see here, is in 10, 20 TeV for gluinos, squarks. The colored particle reaches are typically in the 10, 20, 25 TeV range. Okay, so for gluinos and squarks, for example, here's where we're sitting from the LHC, and here's the projection from a 100 TeV collider, so in the sort of 20 TeV range. Okay? Now, so that means that if it's around the corner, we're just going to obviously see it, but we're going to take that roughly factor of 5, a little more extension in the exclusions, so that however disturbed we were by our notion of naturalness before, it gets multiplied by a factor of 25. Okay? Okay, what about directly for stops? I won't go through this in detail, but you can see just for sort of direct stop production, the limits go up again to the sort of 4 or 5 TeV range, about that factor of 5 higher than the direct limits that we get from the LHC. And similarly for top partners. Okay, so all these things are going into the 5, 6 TeV range. Okay, so this is something which, if you said, well, we've seen percentage accidents before, maybe it's not a big deal. Okay, now if we still don't see anything, you have to say, well, these are now almost part in 10,000 accidents. Okay, and you can't say that we've seen that many times before elsewhere in particle physics. Now, maybe it doesn't matter. You could say already, if it looked at part in 100 bad, it was already bad. And as we said last week, you've already decided what kind of person you are. Now we're haggling over the price. Okay, but still, it is true that it's forcing us into regimes of tuning. If you imagine these were the theories that are going on that we've not been forced to before in particle physics. Never mind the cosmological constant, of course. Now let's take the opposite end. Let's say we do see new physics at the LHC. There's 2 TeV gluinos right hiding in the data, and we're going to see it soon. Okay, here it's very obvious. Here we also want to go to 100 TeV collider, but for much more obvious reasons. But I just want to pause to comment on this because it's sort of amusing that if we had, 300 GeV gluinos, the way my advisor's generation of people thought would happen, then the motivation for going to 100 TeV would be a lot lower, actually. Okay, so you've already seen this whole huge spectrum. You might immediately want to go do much more precision measurements. The picture of the world people had that you would build a linear collider then and go measure the couplings of the sleptons to percentage level accuracy and verify SUSY relations and so on. That was a reasonable picture of the world if you thought that you were already seeing the 0th order picture from the LHC. Now that we don't have that picture, even if we see something, we're not going to know that we have a right to call it a gluino. We're maybe going to make 100 or 1,000 of these guys if we're damn lucky, okay? And that's not enough to be able to actually say that they're a gluino. We might know that it's a colored adjoint. We might not even be able to really say that it's a colored adjoint with the amount of data that we get. We can see enough to make a discovery, but not enough to say what it is. Then what you want is the 100 TeV collider to get you the rate, okay? And if you remember from Hadron Collider 101, the rates at Hadron Colliders scale roughly like the 4th to 5th power for heavy states, scale like the 4th to 5th power of the center of mass energy. So the factor of 7 gain is a huge gain in the rate at which you produce these things. So you would have a factory for these guys at 100 TeV. And there are other interesting cases. Again, if we imagine, let's say just at the 11th and a half hour, we saw something like natural SUSY. So stops are light, but the first 2 generations are heavy. Okay? Maybe we even miss the stop. But anyway, so we'd make the stop at the 100 TeV collider. But what about the first 2 generations? This is an example where the reach for a 100 TeV collider is much larger than the LHC, because you can look at something like associated production, where you make a gluino that would be lightish, let's say 2 or 3 TeV, in association with the light 2 generations. Okay, and here the reach goes all the way up to around 35 TeV for the first 2 generations. So you're not pair producing them. You're making one light guy and one very heavy guy. Okay, so it's the T-channel process where you make a light gluino and the very heavy scalars. And this goes all the way up to around 35 TeV. So that really whomps the reach that we get from the LHC. All right. Now, something else that you know, especially if you're a model builder trying to hide supersymmetry or other natural solutions to the hierarchy problem, is that often, especially since you're dealing with colored partners, you can try to find theories where they're there, they're around, they're light, but they somehow decay in complicated ways. R parity violation, more complicated scenarios. So they're just hidden in the hadronic muck. All right? Now, and you see that just emphasizes the sort of fundamental sense in which making these particles at a hadron collider is an indirect test of whether or not these particles have something to do with the hierarchy problem. You might even make these colored particles, but until you've verified for sure that they talk to the Higgs and they have something, and their couplings are related to the top and so on, you don't really know that they have anything to do with the hierarchy problem at all. What you really like is something that's absolutely directly checking the coupling of new states to the Higgs. And that's exactly what a Higgs factory does, okay? So let's say we have, I'll take the concrete example of stops. Stops just have nowhere to hide. You can make them decay in 30 jets, okay? So totally, make it totally invisible, and it doesn't matter. They will still, if they talk to the Higgs, they have to have a big coupling to the Higgs, they'll still give you a shift, for example, in the Higgs to glue-glue coupling. Or they give you a shift in the S&T parameters. And those are things that you can measure at the Higgs factory and on the Z-pole, and they give you reaches already into the, a TeV 1.5, 2 TeV range. But I emphasize that this is something completely model independent of how it decays. You cannot hide this in hadronic muck. Okay, so that's another complementary piece of, very important complementary piece of information we can get from a Higgs factory. And finally, let me make the following comment about naturalness before we switch finally to, at the end, to dark matter. You could say, look, it's 2020, we haven't seen any new particles at the LHC. Isn't this all sort of crying over spilled milk, right? Won't we already know that this idea of naturalness is just wrong, right? It's already percent just wrong. Now you're arguing whether it's good or bad. But do we really need colliders to further beat an already dead horse, right? That it's already a wrong idea, even though it's only a percent. But that's already a pretty good clue. And of course, the answer is it's certainly both theoretically and experimentally no, because we already have examples of theories that people wrote down long before the LHC turned on that were perfectly compatible with what we see so far. Now, it's true that they're not particularly popular. Well, they weren't particularly popular 10 years ago. They're more popular now, okay? It's true that they look a little Baroque. It's true that it's not the first thing that you would write down. But it's also true that it's possible for the top partners to just not be colored, as we heard at some length last week. But here's another kind of inevitable, here's another bit of inevitability that you have to have. If you have some kind of partner that's giving you a diagram like this that removes the ultraviolet sensitivity associated with the top, with some coupling here that has to do with the top Yukawa coupling. Maybe this stuff is not colored. Maybe the 3 comes from some partner mechanism, as we talked about, as you heard about last week. This diagram means this diagram must exist. Okay? You just take the same vertex and attach it to the top. So there's a completely inevitable shift in the Z-Higgs coupling, because this gives you the d mu h dagger h squared operator. And you have to be able to produce these guys at least in vector boson fusion type processes like this at 100 TeV collider. Okay? So, in other words, if this theory is sitting around with like 400 GeV top primes, totally natural, missed at the LHC, then it'll give you a big shift in the Z-Higgs coupling, at least at loop level, and this direct reach. And in fact, in concrete theories of this sort that you write down, you can get much larger effects. So many theories like this are paired with the general idea that the Higgs is a pseudo-Goldstone boson. As we talked about right at the beginning, it's perfectly possible for what we're going to know directly from the couplings of the Higgs to electroweak states that it could be about as elementary as a pion without a problem. Okay? And so the only way, when we say that all naturalness theories are in trouble at the LHC, it's all indirectly from the assumption of colored partners, right? So you can imagine a theory of the Higgs as a pseudo-Goldstone boson with uncolored top partners, and this theory is totally fine from the LHC, but it still predicts these 10%-ish and roughly that scale deviations in the Z-Higgs couplings. So if you go measure the Z-Higgs coupling and you don't see it, you're forcing, for example, the decay constant associated with these Goldstone bosons to go to like a 3 TeV scale, right? And that means that even this theory, which is pseudo-Goldstone, uncolored top partners, all of that stuff, even this theory, directly from how the Higgs talks to electroweak states, would be forced into the 0.1% level of tuning, okay? Or you flip it around. It could be completely natural, but then we'd have to see a big shift in the Z-Higgs coupling, easily accessible. But even in these cases where the effect is radiative, that unavoidable diagram that I talked about before, then the effects are big enough that you force these particles to be to cover the range in which they would really be natural. Okay? So even in the most indirect possible way, they have to be accessible in how they shift the Z-Higgs coupling. And this is, I apologize, another busy plot. but the particles have to be light enough that you can directly produce them at a 100 TeV collider. Now, what I will say is this is maybe the most important, the important feature of this sort of analysis, that even in these kind of theories, the important claim is that even in the hardest cases, if the shift in the Z-Higgs coupling is sort of barely visible enough to be seen at the 2 sigma level, the particles have to be light enough that you can discover them at 5 sigma at a 100 TeV collider. So again, they give you a shift in the Z-Higgs coupling, and then by going to 100 TeV, you can verify that that's actually what's going on. If these top partners are electroweak charged, not colored but electroweak charged, then you actually get a very strong probe of them from how they affect other things, like how they affect Higgs to gamma gamma. Okay, they won't affect Higgs to glue glue because they're not colored, but they can affect Higgs to gamma gamma. And again, that pushes you, these are sort of contours of tuning, if you like, just what we get from the shift in Higgs to gamma gamma. It forces you into the sort of 10% range for tuning there. You'd really want that thing to be of order 1. And they also give you shifts in the S&T parameters that, again, force the particles already into the sort of into the TeV scale. Even when we're going to all this distance to make it uncolored, not visible at the LHC, all of this structure, and this shows that we can even push these things well into the unnatural territory. All right, so that's all I want to say about naturalness. The summary there for me is that what's the problem? What's the issue with the LHC? The issue with the LHC is that the models that were popular in the 90s are in a lot of trouble, okay? And the models that were not popular in the early 2000s are now slightly popular because they're not dead, all right? Now, of course, SUSY is also not dead. It's just much more tuned than anyone expected it to be. So whatever's going on, maybe something small is wrong, and they're really just lying around and we're missing them, and you just take this big factor of 7 leap in energy and you for sure make them, and you'll see lots of evidence for their existence by more precision measurements of the Higgs. Maybe there's some more exotic, standard, natural possibility going on, like neutral naturalness, and then the sort of bulk, where those theories are actually natural, you do not see them at the LHC, and you just cover them with the Higgs factor in the 100 TeV collider, and even push them into unnatural territory. All right, so let's finally talk about dark matter, and this is something that we stressed last week and this week a couple of times. So WIMPs are still the only calculable models of dark matter that we have. The only models where we get to remove the uncertainty with initial conditions by assuming that the dark matter was once in thermal equilibrium with everything else. And as we said already a few times, if the W in WIMP stands for weak, the weak interactions, then it could trivially be that the WIMPs are at a few TeV and completely inaccessible to the LHC. So we gave examples. This is not something where the theorists are trying to hide the dark matter. This is something a calculation you could have done, probably somebody did do in 1979. What mass would an electroweak doublet have to be thermal dark matter? 1 TeV. What mass would a neutral triplet have to be dark matter? 3 TeV. Okay? And those things are inaccessible, completely inaccessible to the LHC. And as we stressed before, they're even invisible to direct detection because the leading interactions with the Higgs are just not there. Everything at tree level, everything is mediated radiatively. And I think the number I put on the board there when I was talking last week, that the cross-section was around 10 to the minus 46 centimeters squared, is wrong. It's actually more like even 10 to the minus 47 centimeters squared or even smaller. So they're really even at or below the famous neutrino floor. So we won't even see them with direct detection. Okay? So what do you need in order to be able to produce these particles at colliders? You need to be able to have a collider that produces 1 to 2 to 3 TeV weakly interacting particles. The LHC is great at producing 4, 5, 600 GeV weakly interacting particles and 2, 3 TeV strongly interacting particles. So you need to go up from that by your factor of 5 to 10 to have an electroweak factory. All right, now just a little bit more, a little bit more basic physics. Let's talk about those very simple cases. The very simple cases were the very simplest cases of dark matter I'll just go back to the board here, but don't raise it, I'll just write, were something like a Higgsino or a Wino. Okay. Does anyone know why it's, so I said that like a TV Higgsino is inaccessible to the LHC. Does anyone know, like, how many Higgsinos are we making at the LHC? When I say it's inaccessible, are we making no Higgsinos? If you have a TV Higgsino, how many people know roughly how many of them we're making every year today? Okay. If you're a particle physicist, you need to know these numbers, okay? So we're making, definitely not less than one. We're making a lot of them. Actually, that's a little exercise for you, okay? From what Leon Tal told you, you should be able to easily figure out how many Higgsinos we're making at the LHC. It's many, many more than one, okay? We're making a lot of Higgsinos at the LHC. Not tens of thousands, but we're making lots of Higgsinos at the LHC. So what's the problem? The problem is that they decay in an absolutely horrible way, right? So they're very difficult to see. Now, why is that? So what does it look like? Let's say I give you an electroweak doublet, right? What does the spectrum of the theory look like? What's in an electroweak doublet? There's a neutral particle and a charged particle, right? Of charge 1. What are their masses? If I say the mass of the doublet is 1 TeV, what are the masses of those two particles? What do you think? They should be degenerate, right? You know, they don't know about electroweak symmetry breaking. The mass is much bigger than a TeV. So you would think, thank you, but I'm going to need it back down in a sec. You would think that the masses are equal, and they are to very good approximation, but they are split. They are split by electroweak symmetry breaking, after all. So there's no symmetry that rotates them into each other. They are split. And so whatever your representation is, you can draw a diagram that looks like this, which maybe has W's and Z's in it, and photons or hypercharge, right? But in terms of the mass, I can say W's and Z's and photons in it. And these diagrams will be different for the neutral and the charged states, right? So there's some splitting. Now, what do you think the splitting is? How would you estimate the splitting? Do you have some rough idea what the splitting is? Well, first of all, there's an alpha in front of it, right? So delta M is going to be around alpha. So what do you think it multiplies? So I'm going to try to confuse you a little bit, okay? So what do you think should happen as the mass of the particle goes to infinity? Way heavier than the weak scale, right? Oh, you might think the splitting should vanish. So this is what I would have guessed without thinking about it much. Okay? Is it alpha? Well, there had better be a 1 over m, right? And what should go upstairs? mz squared, right? It should vanish, wz squared. It should vanish in the limit as you don't break electroweak symmetry. Okay? Wrong, right? Now, this is the reason I'm bringing this up is it's a general important fact that expressions like this, you see, mz squared, that's something that occurs as a parameter in the Lagrangian. So this is a formula that you would say in a fancy way, this is a formula that's analytic in the couplings that appear in the Lagrangian, okay? Things that are analytic are always things that come from short distances. Everything which is generated by physics at long distances is not analytic in anything. It's not analytic in the couplings, it's not analytic in the momenta, it's not analytic in anything. That's the sort of hallmark of something which actually comes from long-distance physics. This is a long-distance effect, okay? The W and Z masses at much longer distances compared to the mass are actually are generating this effect. If I had some higher dimension operators, the higher dimension operators could split the states. For example, if it was a doublet, if a doublet psi could have the operator h dagger psi up, h psi down, say. Okay, psi up and psi down divided by some high mass scale. It doesn't have to be the mass of the particle. And you see this would be something that goes like v squared over lambda. Right? So that's like your rough intuition. But this is not like that. In fact, the effect goes like alpha times mz. Okay, there's no mass suppression in it all. And the non-analyticity is that that mz doesn't occur in the Lagrangian. It's really the square root of mz squared. Okay? So that's something that isn't analytic. That's a very formal way of saying what it is, but what is this effect physically? It's a very pretty and beautiful effect, which I'll say roughly, and then I'll leave you as an exercise. I'll give you the right answer so you can know if you're doing it right, but I'll leave you as a nice exercise to think about on your plane rides or train rides or bike rides home to figure it out. But this is the physics. Imagine you have the charge component of the doublet. Okay, you have the charge component of the doublet. The charge component radiates a photon field. So there's a photon electromagnetic field around it, okay? So that's the usual photon electromagnetic field. Photons. So this is the charge guy. The neutral guy, let's say SU2 is not broken. So the neutral guy, what is a neutral guy shining? It's shining the Z, all right? I'm saying it a little loosely. There's really the different components, but loosely, it's shining the Z. So it's got the Z field in front of it, right? Now, there's some electrostatic energy that's stored in this electric field, right? Do you remember how that electrostatic energy goes? It's divergent at short distances, right? But it goes like alpha divided by the short distance cutoff, right? So if I put some short distance scale here, then the electrostatic energy, if you integrate the electric field squared, this goes like alpha over A, where A is this length scale that I cut it off by. All right? Now, that was a famous fact about the self-energy of the electron that was ultimately fixed up by particles and antiparticles and all of that stuff in field theory, right? So these linear divergences disappeared, and they were replaced with the logs that we're used to in field theory. But here, there's a different effect. You see, at very short distances, you don't see that electroweak symmetry is broken. So the short distance contribution here is identical to the short distance contribution here. But there's a difference from long distances, because at long distances, the Z contribution shuts off, but the photon contribution keeps going. Okay? So in this mass difference, there is something which is the extra electrostatic energy stored in the photon electric field, which is not there for the Z. Okay? So in the mass difference, for delta M, you get something that goes like alpha times mz. Okay? That's exactly what this 1 over A is if you now cut it off at around the scale associated with the Z. Okay? Now, this is something that you can definitely convince yourself is true by looking at this diagram without actually calculating the loop. Okay? And that's what I want you to play with on your train, plane, bike ride home, is to understand how it's a very standard and famous thing about how when particles are heavy, you can interpret pieces of loop diagrams as coming from these classical self-energy effects. And just so you know whether you're doing it right or wrong, let me give you the answers. So for a Higgsino, so an electroweak doublet with hypercharge, a half, delta M, always in units, so I'm going to say delta M is alpha mz over 2 times something, and the somethings are the following. And I'm just giving you the dependence on the Weinberg angle, and this is all you need to know to know if you're doing it right or not. It's sine squared theta Weinberg for a Higgsino, and it's cos theta Weinberg times 1 minus cos theta Weinberg for a Wino. And if you have energy to do a charged triplet, so a triplet of charge 1, of hypercharge 1, so that there's a charge 1 and charge 2 state, the mass difference between the plus and the 0 is 2 times 2 plus cos theta Weinberg times sine squared theta Weinberg over 2. And for the doubly charged minus the singly charged, it is 2 times 2 plus 3 cos theta Weinberg times sine squared theta Weinberg over 2. So these are various sort of simple theories for what these electroweak states could be. They all contain something neutral. And we have all these corrections that are parametrically set by alpha mz over 2. I've given you these dependence on sine theta Weinberg so that you can make sure you understand, if you try to do the calculation, where all the different pieces are coming from. They're coming from W's, Z's. You have to stare at the pictures and figure out how to extract these classical pieces from them without doing any work. All right, but anyway, that's the basic physics, all right? And so these are very small splittings. They're roughly in the hundreds of MeV range, but in detail, for the Higgsino, this ends up being 330 MeV. This is, for the WeNo, it's 160 MeV. And in these other cases, just for fun, it's 500 MeV, 800 MeV. Okay, so this is not a situation then where you're like you're used to, where you produce a charged state and it decays to a neutral state. You see a lot of missing energy. This is not like that, right? The states are very nearly degenerate with each other. And so how do you look for them? So let's say, first of all, let's say I produce the WeNo. What happens? What happens if I produce the neutral WeNo? Nothing, right? The neutral WeNo is the dark matter here, right? So it's just stable, just escape state attacker. I see nothing. What if I produce the charged WeNo? Then, because this mass splitting is so small, it travels a macroscopic distance before it decays. Do you know parametrically what it is? What's the lifetime in terms of delta M? I mean, not numerically. What is it parametrically? What's the formula? It's around delta M to the fifth over MW to the fourth. Okay? Very much like neutron decay, right? So, and if you put in the numbers, this travels, its C tau is around 10 centimeters. Okay, so that's nice. C tau is around 10 centimeters for this guy. That's long enough that the charged part can actually, you see it in the tracker, right? So you see a charged track, and then what happens? It decays. What do you see? What does it decay to, first of all? Just a pion, right? Actually, it has barely enough room to spit out a pion, but it does. 160 is bigger than 135, okay? So, but it gives you a very soft pion, which you don't see, okay? Just spirals, and you don't see. So what you see is what they call disappearing tracks, right? So it just goes, and then it just stops. A very spectacular signal, right? So that helps a lot to look for it. What about the Higgsino? Here it's much harder. Just this lousy factor of 2 means that what's its C tau? Its C tau is like half a centimeter, right? It scales like the, it's like almost a millimeter. It scales like the 5th power of delta M. So just that factor of 2 means that it travels 32 times less far, and so it's much harder to look for it in the tracker, okay? And these other cases are, you don't get any leverage out of that, all right? So what's the broad thing you're looking for whenever you're making something invisible at a hadron collider? You have to tag it with something, so it's a monojet or a monophoton signal. Okay, so you have to radiate off a hard jet from the initial state, in this case, because the particles are neutral. But if it's in the particular case of a WeNo, you get a little bit more leverage from the fact that the delta M is small enough that we get the displacement. So can I get the screen back down? And I'll just say this, and I think we'll stop there. Oops. All right, so this is the kind of reach that we get from the LHC versus 100 TeV collider. And remember, the figure of merit, what you're after for a WeNo is roughly 2.5, 3 TeV if it's a thermal relic. Okay, so 2.5, 3 TeV, totally hopeless at the LHC. But it's, and the sort of differences are, this is a 5 sigma band, 5 sigma discovery, sort of 2 sigma exclusion. There are some assumptions being made here on how well you can control the systematics and take advantage of the disappearing tracks, but it's fairly conservative. And 3 TeV is coverable, okay? It's quite robustly coverable in this case. So you can get to the 3 TeV WeNos. The Higgsinos are just, getting to a TeV is hard. So that's what you need for a thermal relic. And again, these are the very first rounds of analyses, so you might be able to do better, but you can get to sort of 800 GeV, okay? So not quite all the way there for if it's completely a thermal relic. Okay? If it's even 50% of the dark matter, no problem. Okay? But so here a little bit more thinking needs to be done. But it's close. And again, of course, it's a big leap relative to the LHC. That's the thing to keep in mind, is that the 100 TeV collider is an electroweak factory. And we're starting from the worst, hardest possible case, where we have the huge rate for producing them, but because of these tiny splittings, we have to pay the extra factor to radiate off the extra jets. Okay, but even these very vanilla cases that we know is covered, the Higgsino is almost covered, and maybe with more thinking, we could really even more robustly cover that case. Now to something a little easier to think about. Let's say it's not just one state there, but you have a whole electroweak sector. So this is what would happen in split SUSY, for example. Okay? In split SUSY, if the bottom of the spectrum is in this TeV range as dark matter, the gluino is somewhere around 10, 20 TeV. Remember, 10, 20 TeV is no problem at heaviest. 10, 20 TeV you can make directly. But even the electroweak part, now you're making so many 3, 4 TeV electroweak states that if there are reasonable splittings between their masses, that you're looking for the usual kind of signals. Leptons plus missing energy, same sign, opposite sign, trileptons, and so on. But now the sort of mass reach is really robustly going into the multi-TeV scale. Now we really take advantage of the fact that we get an electroweak factory, and so we can really probe this very robustly. So I would say that every reasonable version of a split SUSY that I could think of would be easily covered by the 100 TeV collider. So this is a summary for dark matter. I think there's a quite robust coverage for WIMPs in a whole bunch of different scenarios that go into the TeV, multi-TeV range, except for the Higgsino, which has some challenges. And if we have these cascades, we have more stuff in the electroweak sector, then we really go into multi-TeV everywhere very, very robustly. So again, it's not a no-lose theorem. A WIMP could be some crappy particle annihilating to taus, and then we're not going to see that at 100 TeV collider. But it is interesting if we take the simplest theories, most obvious things, which are by no malice invisible to the LHC and to direct detection experiments, that we can quite robustly cover them with the 100 TeV collider. All right. So that's really what I wanted to say about these things where there are important physics questions where we get some very solid answer to these questions from the degree of leap in precision and energy that we get from these guys. So the final comments are, will it happen? Might it happen? As I'm sure almost all of you know, our friends at CERN have been talking about it for a long time, for the past several years. What particle physicists like to see more than anything else is maps of the world with giant circles on them. And so there's the picture of the area around Lake Geneva, and so there's the LHC, and this is what I think in this case an 80-kilometer tunnel would look like, and you do have to go under the lake. And our friends in China are talking about it, and this is actually by now an old picture. This is one of the sites that they're thinking about now. There are others, but this is an area around 300 kilometers northeast of Beijing. It's where the Great Wall starts. I'm told there's no pollution because the Communist Party officials go there for their summer holidays. So it's very beautiful and so on. I've never been. But there's a 50-kilometer tunnel and a 100-kilometer tunnel. And this at CERN, the whole program is called the Future Circular Collider Program, so FCC. In China, it's the Circular Electron-Positron Collider, or the Super Proton-Proton Collider. And one of the reasons this is out of date is that our friends there are really almost exclusively talking about 100-kilometer tunnels now. So we'd always have to draw these pictures, and I would always say 100 kilometers, and they would always say 50 kilometers. But now almost everyone's talking about 100 kilometers all the time. So what's the only problem? The only problem is that it costs 10 billion in your favorite units. Okay? And is this a problem? Well, it's an incredibly naive thing to say that these things now cost, oh my God, that it costs, the LHC costs a few billions of dollars, these things are going to cost tens of billions of dollars. Yes, it's true, but there are decades between when these projects, these projects are separated by decades. If you went back and told someone in 1950 that, my former crappy Mitsubishi cost $5,000 to buy, they would be very shocked, right? The world is getting wealthier. It's the ratio that matters, not the absolute cost. And this is something that, this is a little table that Yifang Wang, who's leading up this effort in China, made, which I like very much, which just shows that the cost of accelerators compared to GDP has been basically constant for the last 30, 40 years. And it's always roughly 10 to the minus 4, okay? So, the LHC is around 310 to the minus 4 European GDP. The ILC is 210 to the minus 4. Everything here. The SSC was around 10 to the minus 4 when it was canceled, right? So, and if we do these things, it'll still be around 10 to the minus 4, okay? The amusing thing in China, of course, is that when they made their little electron-positron collider in Beijing in 1984, was also 10 to the minus 4 of Chinese GDP back then. So for the same ratio, they can go from having a little 250-meter E plus E minus collider that puts them on the map to having the machine that leads the world for the next 30 or 40 years, right? Okay, now, is 10 to the minus 4 too much? Maybe it's too much. That's something that we should decide and talk about, but it's not something new that we're asking. We're not talking about something that's qualitatively different than what we're talking about before. And, in previous epochs in history, people have thought that fundamental advances in science were made much more, were worth much more. I always used to talk in talks like this about how much Tycho Brahe's king gave of his GDP to Tycho Brahe to give him this island where he could sit there and make measurements of the motions of the planets for 30 years. That led to the modern, led to Kepler figuring everything out about orbits not being circles and ellipses and all the rest of it. So obviously a wise investment. And, just as a joke in talks, I would say, I don't know, that was probably like 10% of his GDP. Well, some historian emailed me, and actually it was around 2% of the GDP. So it is, anyway, so I was joking. I didn't think it was remote, I didn't even think it would be as high as 1%, but it was around 1% or 2 of Danish GDP back then. And, it was probably worth it. Okay, so it was about 100 times more than we're talking about now. So, but in any case, that's not really relevant to this discussion, but we're not talking about something qualitatively different compared to what we have done before. All right, so now I think I've gone over time, so I won't go through this too much. We can maybe talk about it over lunch if there are people who are interested. There are a lot of common objections. There's no point to planning ahead for these things before we get all the results from the LHC. The answer to this is, while it's definitely true that we're in the most exciting phase of the LHC, no matter what the LHC sees, we already know there are questions that we're not going to get the answer to them from the LHC, important questions we're not going to get the answer to from the LHC, whatever happens. If we see nothing but the Higgs, totally obvious. We have to study the Higgs and put it under a more powerful microscope because, as I stress, we only get a fuzzy picture of it from the LHC. Okay, so in this case, it's obvious we need to know more experimentally. What if we see new particles? Well, we talked about that too. In the case of gluinos, let's say we see stops. Well, we'd only put that in quotation marks at the LHC. We have no idea they're actually stops because we don't make them with enough rate. So you need the 100 TeV collider to up the rate by a factor of 1,000 so that you make a factory of them and you can study them and figure out what they're telling you. So we don't need to wait to see which one of these possibilities is realized. Whatever happens, there are important questions that we're not going to get the answer to. And so we can start planning and thinking about it now. Another common thing, if we only see, this is all a crazy pipe dream. If you only see the Higgs at the LHC and nothing else, we can never convince politicians to build machines. So this is just so stupid to be thinking about these things. Well, I find this argument hilarious because, especially in this country now, it assumes an enormous amount of intelligence on the part of politicians. Imagine they're sitting there in Washington and they're like, looks like naturalness wasn't right. That's very surprising. I really thought the stops would be around the corner. I don't know, right? They have no idea what the hell's going on. It's a job of scientists to tell politicians what's scientifically important, And if the scientists think it's important and you can convince the world and the country to think it's important, then we'll do it. If we can't, we can't. But they're not sitting there with some sort of prejudgment about what's scientifically exciting or not. What I find about people who make this argument is that it's actually not the politicians. And they might be a little embarrassed to say it. It's themselves. They don't think there's a point to continuing. They think, oh my God, we're not going to see new particles. I wanted to see a plot with giant spikes in it, just like they did in the 60s. And that's not going to happen, so I'm a little worried, I'm a little depressed. And instead of saying it's me, I'll blame the politicians, okay? Well, we're in a different place intellectually now on the subject than we were in the 60s. In many ways, the stakes are much higher now than they were back then. There are big structural issues on the table now compared to the issues then. But the nature of the kind of experiments we have to do and the kind of questions we have to ask and how long we have to wait to get the answer to the question is just longer. That's been the typical way it's been in fundamental physics for a long time. Okay? And people have to expect that it can take decades to figure things out, that you have to do difficult measurements for a long time. That's why it's a tough business. No one promised you a rose garden, but that's why also it's an important business. Okay? And it's a deep business. And so if we believe that these questions, the ones that I talked about, are important, then we just have to tell the world, we have to tell people, we have to tell politicians, we have to tell them why we think it's important. I think it's important. I think it's worth spending decades of my life on. Many of my experimental friends think they're important. They're the people who even matter more than me because I can go fool around on the side every now and then, right? They have to devote their lives to doing this. There's enough of them who think it's important. Great. We have to go tell the politicians and hopefully they will agree with us. But I think the intellectual case is like super strong, okay? We are extremely theoretically confused about deep things and we can do something about it experimentally. So, duh, you should just go ahead and do it. Okay? Analogous to this, if we don't see new physics, the whole thing's a big failure, right? Oh, it'll be such a waste, tens of billions of dollars. And what's the problem with this? The problem is the assumption that this word means new particles, okay? And as I've stressed many times, just learning anything about this strange point-like particle, if we learn nothing else, will tell us a lot about the way the world works. There's no sense in which these things could be a failure because we're learning something very fundamental about something we're very confused about. And there are concrete results that experimentalists will get, concrete facts about the world that we will get that are important and will be as important 10,000 years from now as they are today. Finally, what about the ILC? Okay? This is actually a very important question for geopolitical reasons, but scientifically, it would be, both scientifically and geopolitically, it would be awesome to have an ILC, okay? First of all, now, for purely measurements of the Higgs couplings, these circular Higgs factories do similar measurements, and they broadly give you the same kind of sensitivities as the ILC. People are now talking about perhaps staging the ILC, even starting with lower energies down at 250. Those things would be very similar, very, very similar to the measurements you get at circular colliders. But something worth remembering is that eventually, to get to super high energies, we're not going to do it with proton-proton machines. We'll eventually have to do them with electrons. There are these ideas like plasma wake-field accelerators and things like that that could, in principle, get you, factors of 1 million larger electric fields that could accelerate particles. That's a sort of limit around alpha cubed inverse, around 1 million times bigger than the electric fields we can get in materials that are limited by just dielectric destruction of the material that's hosting the electric field. So that gives a limit to how in normal materials we can accelerate things, but in principle, in plasmas, you can separate charges by a lot and get huge electric fields. The electric fields are ultimately limited by Schwinger pair production, but if you look at the sort of ratio of the biggest electric fields you can get that don't destroy materials to the biggest you could possibly get, it's roughly a factor of alpha cubed, or 1 million. So you can in principle get much, much higher energies, but those things, they're still a long way off. It's very difficult to accelerate particles many, many times and get high luminosities like that. But if they do start working, even partially, you'll use them as afterburners on linear colliders, okay? So there's there's an ultimate path forward for very, very high energies eventually, where you definitely do not want to lose linear collider technology. We're going to need linear colliders, and if we don't have linear colliders on the planet, then this whole generation of people who knows how to build them will be gone. It'll be very hard to keep it going. So it's great for scientific reasons, and naturally for geopolitical reasons, especially in China. In my view, nothing would more quickly guarantee that China built a circular collider than Japan building a linear one. Okay? So I'm a very big fan of the ILC for scientific and geopolitical reasons. All right, and finally, I alluded to it, instead of bigger accelerators, shouldn't we wait to develop some revolutionary new methods and do it cheap? And I just quickly alluded to what those methods were, and it would be fantastic if we could make them work. It's not something which is even, as far as I can tell, even on the horizon, to have an idea of how you could get the luminosities high enough. Again, the problem is you can get huge electric fields that can give a particle a big kick once, but then, you have a bunch of them, you give a big kick and you spray them out in some horrible way, and it's hard to keep them collimated and kick over and over and over again. Okay? So while you can get very large gains in small distances, it's hard to do it in a coherent way. And this has been something that's been said about particle experiments for decades. Our friends in condensed matter physics told us when the SSC was being built that we should wait for high TC magnets to come along that would revolutionize everything in the world, of course, but in particular make accelerators much cheaper. Well, it's 40 years later, they haven't happened, okay? And it would have been a very bad idea back then to listen to them and stop everything and wait for it, okay? So we do what we can at any given time. We make, if there are reasonable things that seems like we can wait, great. But I don't see any reasonable thing out there that's a feasible alternative to doing this, and so that's the case I think we should make. All right, so that's all I wanted to say. Let me just end by thanking you all for coming to the school. I really hope you had fun with each other. I hope it was an intense couple of weeks. I hope you got exposure to all kinds of physics that you haven't thought about before, and that you keep in mind what I told you on the very first day, that it's an ideal time to be your age, because there's all kinds of wrong things you don't have to learn, and there's all sorts of opportunities for very interesting, totally new directions, some of which have been lectured on at the school that might carry the field forward in the next 20 or 30 years, and it's really your job to do it. So thanks a lot.